Hi everyone. Uh, I thought I'll discuss a very interesting but a simple question that I posted sometime on LinkedIn some time back. So the question is that you have a LTS, a linear time invariant system with an impulse response h of t. It turns out that if you feed a signal x of t as an input to that filter or to that system, the output is also x of t. Now, the interesting thing, the solution for this problem is quite trivial. But here in this problem, it's given that the impulse response cannot be an impulse, right? So now the question that's being posed is that are there any signals and their corresponding impulse responses or a system's impulse responses which will obey this condition where the output will exactly be equal to the input, okay? And it doesn't depend upon, it doesn't get scaled or it doesn't get altered by the impulse response. So that's what the question is. So that's what I've written here. Are there any signals and systems? When I say systems, here it is h of t, the impulse response, and a signal pair which will obey this condition. That's what we need to figure out. Now, first, I'll just remove the trivial solution. We know that if y of t equals x of t, such systems are called identity systems. I mean, systems whose outputs are exactly the same as inputs. And for these identity systems, the standard solution is the impulse response is an impulse itself. Okay, that can be easily derived by looking at the Fourier domain or the Laplacian domain. So if you see the Laplace transform of the output y of s is simply h of s times x of s. I mean, I can express this in terms of Fourier transforms also. So y of f equals h of f times x of f. Okay, so now it's given that y of f equals x of f, therefore h of f becomes equal to 1. And if you take its inverse Fourier transform or inverse Laplace transform, the solution is delta of t. That's a trivial solution for this problem. But it's specifically given in the question that that's not an allowed solution. So then what could be the answer? The problem can be very easily understood or can easily solved, and you should just think what was my thought process about setting this question. Because I was teaching filters, and if you think about this, let's assume x of t is a band pass signal, meaning its energy is concentrated only over a narrow band of frequencies. Okay, outside that band, its energy is zero. That's what I've shown here. X of f is a band pass signal, and here the signal's Fourier transform is not even symmetric around the origin. So I'll probably discuss in more mathematical detail what do I mean by all this. Here it's assumed that you have a basic understanding of signals and systems. So which means this such signals are complex signals. In time domain, it will be a complex signal. So this I've just assumed a very generic representation of the Fourier transform. Let x of f be a band limited signal. Okay, a band limited signal is one whose energy is concentrated over a narrow range of frequencies. Now, by looking at this figure, I want an output y of f to be equal to exactly this. Then what are the possible solutions of h of f? One can immediately think of, I just need to design a filter whose gain is supposed to be 1 in this range of frequencies. That's it, right? So if you pass this signal through a filter whose transfer function is going to be constant in this range, then the output is also going to be the same signal. It's going to pass the signal as it is. So it's a frequency selective filter. Okay, so but here the ideal condition, because I want x of f to be exactly equal to y of f, h of f has to be 1 within that band where your x of f is non-zero. That's the only condition you'll have to satisfy. So I can assume some h of f which is flat in this region minus b3 and b4, and it is assumed that b3 is greater than b1 and b4 is also greater than b2. So mod of b3 is greater than b1 and similarly b4 is greater than b2. which means I'm able to pass this signal fully through this filter. That's all this condition is stating. Okay, so the bandwidth of this filter has to be greater, the bandwidth of this, or the band of this filter should be greater than the input signal's band. And it should be equal to 1 in the region where your input signal's energy is finite. Now, if you satisfy this condition, then I'll get the output to be exactly equal to the input. So that's it. I've just solved the problem. All I'm trying to say is that you take any band limited signal, then there are infinitely many possible solutions which will satisfy this condition, where your output will be equal to input. Any band limited signal, if you pass it through a filter whose characteristics remain flat in the region where the signal is non-zero. Okay, in the region where the signal is, the only condition you have to satisfy is h of f is supposed to be flat in this region. That's it. I mean, it can be anything other outside this region. It can have any different shape outside this region. It has to remain flat only within this band of frequencies. And if you satisfy that condition, then the output will exactly be equal to the input. So now immediately you can see there are infinitely many solutions possible, right? All I need to do is that ensure that it is 1 in this region, and whatever shape, it can assume whatever shape outside this band. Or you can think of band pass filters, or filters with a finite pass band, and it's 0 elsewhere, but of different bandwidths, as long as the bandwidth is greater than b1 plus b2. Okay, any filter that satisfies this condition will give me this result, where your output will be equal to the input. So that's what I've been discussing. It's a very simple problem the moment you think of it from a filter point of view. So if you put some conditions on the input, the condition being x of f, your input signal is band limited, its energy is concentrated within a small range of frequencies, then there are infinitely many possible solutions for this problem. It's a simple filter design problem, right? You just have to pass that frequencies as it is. So now we can take many interesting examples. The one example is, let's assume x of f is a band pass signal, a perfectly brick wall band pass signal, which means it is constant within the range of minus b to plus b. The inverse Fourier transform for this is a sinc function. Okay, again, don't worry about the mathematics of it now. If you don't follow the math, I'm just wanting you to understand it intuitively. Later, when I offer a course on signals and systems, we can logically arrive at all these equations. The math will not scare you at that point. Okay, so right now you can just think like this. For a time domain pulse signal, the Fourier transform is a sinc, and therefore if you have a time domain sinc function, then the Fourier transform will be like a pulse function. So this is like a band limited signal. Okay, so then any filter whose bandwidth is greater than b, here I've assumed the filter to be of bandwidth b1 greater than b, will satisfy the condition y of f equals x of f. The important thing is the passband gain is supposed to be 1. That's it. So I've written it here in terms of x of t is a sinc function, h of t is also a sinc. If you take inverse transform of h of f, it's also a sinc. Okay, so if you satisfy this condition, then the convolution of this function with this function will also be a sinc function equal to this in time domain. In time domain, it might look very complicated because you have to visualize convolutions of two sinc functions. But if you look at it as multiplications in frequency domain, it's very trivial. Okay, it's multiplication of just two brick wall filter functions, and it's very easy to see that in frequency domain. And one interesting result to keep in mind here is that sinc function is probably the only function where you convolve it with itself. So that is, if you convolve two sinc functions, so sinc x convolved with sinc x, you get the output also to be a sinc function. Okay, Gaussian functions also satisfy these conditions, impulse functions also satisfies this condition, but sinc function is one interesting example which exactly meets this. I mean, you pass a sinc and a sinc with a passband gain of 1, let's say in frequency domain, you get an exact sinc at the output. Even Gaussians, the shape of the function, the variance will change and all that when you convolve to Gaussian functions, but when you convolve to sinc functions, you can get, with appropriate choice of coefficients, you can get the exact same one of the sinc functions at the output. A sinc function is the only a function other than an impulse which obeys this condition, right? So if you convolve an impulse with an impulse, you get an impulse as well. So all I'm saying here is that sinc function is another function which satisfies this condition. Now this should look a bit intuitive because when I pose this question, that the output is supposed to be exactly equal to the input, and when you take its Laplace transform, if you write it in terms of the convolution integral or convolution expression, this is the equation you get. Okay, you get an equation in time domain. X of t convolved with h of t should be equal to x of f, x of t, or this in frequency domain, the product of the filter response and the input Fourier transform should be equal to the input Fourier transform itself, input signal Fourier transform itself. If you look at this operation in frequency domain, we know that multiplication is not a unique operation. Now, what do I mean by that is that if I multiply two signals x1 and x2, and the resulting signal, let's call it x, okay, I can take another signal x3 and x4 and get xx as well. So that's what I mean. Multiplication is not a unique operation, meaning if I multiply two signals, the resulting signal is not unique. So by looking at this, I cannot precisely say what were the input signals that led to this, right? What were the two signals that I multiplied which resulted in this output signal? You can take some quick examples. For example, say cos omega naught t into sine omega naught t. I'm multiplying these two signals. The result, I can write it as half sine 2 omega. That's a simple trigonometric expression. You get half sine, it's a signal of twice the frequency with a factor of half. I can also take half and multiply it with sine 2 omega naught t and get the same signal as the output. So that's what I was trying to say. It's not a unique operation. Now, Fourier transform is a unique operation, which means every signal is uniquely identifiable by its Fourier transform. There is a one-to-one relationship. That's not the case for multiplications. I mean, you can prove it, even take two real numbers and easily see that multiplication is not a unique operation, meaning if you multiply two numbers, you don't get the number that it produces is not unique, okay? Because different numbers can result in the same multiplied value. That's what applies here at a fundamental level. That's what this problem is, okay? When you first thought of it, immediately you thought the only solution possible is an impulse. That's the most generic solution for this problem. But if you think about it a little bit, then you will immediately see that there are infinite possibilities if you just impose certain conditions on your input signal x of t. So you take a sinc and a filter, you get sinc. The resulting signal will also be a sinc signal. Another quick examples you can think, because now that you can see it like a filter, you can think the input signal to be a sinusoid. If your input signal is a sinusoid, which means its Fourier transform is going to be two impulses at, say, some frequency f naught. Then h of f has to be just filters which are constant in this region f naught. Okay, if I just assume the filters to have a gain of 1 in this band around f naught, then this will pass the sinusoid as it is. That's it. It's just like a band pass filter. Okay, so that's what I was trying to express this problem. You can now think of infinitely many solutions for this problem. I've just discarded impulse as the only solution. Then the intuition behind this is, think of it like a filter. And the filter's response should be 1 in the range where your signal's energy is non-zero. The moment you add this constraint that your input signal is a band-limited signal, then the possibilities are infinite. Okay, so that's it. I'll probably start posting more about signals and systems and some interesting problems in the future. Thank you.